Imagine for a second the ultimate engineering challenge. You're looking up at this chaotic, stormy atmosphere, just completely full of shifting winds and thermal gradients. And somewhere, way out on the other side of all that mess, is a moving target. Your mission? To somehow transmit information right through that interference, and do it without losing the signal. I mean, how do you even begin to shoot a light signal through a turbulent sky and actually maintain a perfect lock on a moving target? And to make this challenge even more insane, we aren't just talking about blasting some massive, powerful beam of light out there and hoping some of it makes it through. No, we're talking about precision, extreme precision. We are talking about controlling the transmission down to just one single photon at a time. Literally, one photon. Welcome to this explainer. I'm absolutely thrilled to have you here. If you're the kind of focused learner who just loves breaking down cutting-edge technology, well, you're in exactly the right place. Today, we're opening up a fascinating mission briefing on the mechanics of advanced laser communication. We're going to look at a highly specific system architecture that was designed to solve this exact photon transmission problem. Okay, let's dive right into this. Here's our tactical breakdown for today. First, we'll define the free space optical link. Then we'll introduce the Jitterbug hub and Solstice node, and walk through the laser operating sequence. After that, we'll cover the jet fighter tracking control, tackle those tricky atmospheric disturbances, and finally finish up with deployment and safety. Section 1. The free space optical link. At its core, what we're really talking about here is a free space optical link. Basically, this is a communication system that uses lasers to transmit data right through the open air. So instead of running heavy fiber optic cables deep into the ground, the air itself actually becomes the medium. The telescope and the laser system act as this physical transport layer. But here's the catch. Because it's open air, it's highly susceptible to atmospheric disturbance. That means the system has to be incredibly smart just to remain stable. Think of it like trying to shine a tiny laser pointer into the exact center of a moving coin from miles away, right through a hurricane. Pretty wild, right? All right, moving on to Section 2, the Jitterbug hub and Solstice node. Now, what's really interesting here is how clearly the responsibilities are divided in this architecture. On one side, the Jitterbug hub acts as the brain. It's the command layer. It manages the pointing, the pulse timing, the tracking correction, and the actual transmission itself. Then on the other side, we have the Solstice node. And this acts as a stabilization anchor. It provides a constant reference beacon, lock confirmation, and feedback. Basically, the Jitterbug hub relies entirely on that Solstice node, just to know exactly where to point. Which brings us to Section 3, the laser operating sequence. Let's walk through this sequence step by step, because it brilliantly illustrates that this isn't just some one-way flashlight. It is a full closed-loop control system. Step 1, the Solstice node broadcasts a steady beacon reference. Step 2, the Jitterbug hub sees that beacon and instantly calculates its alignment error. Step 3, fast steering optics adjust the telescope's line of sight. Step 4, only now does the laser fire its calibrated pulses or even those single photons we talked about. Step 5, the Solstice node detects the light and fires back a confirmation. And finally, Step 6, the Jitterbug hub continuously updates its timing and pointing based on that feedback. So it's just this endless, rapid loop of correction. Now for Section 4, jet fighter tracking control. A lot of the engineering texts actually describe this pointing subsystem using a jet fighter tracking analogy, and honestly, it's incredibly fitting. To catch a moving target through all that atmospheric interference, you need rapid target acquisition and continuous line-of-sight correction. But more importantly, you need predictive motion compensation. The system doesn't just react to where the target was a millisecond ago. Instead, the fast servo loop actually predicts where it's going to be, compensating for motion and drift in real time. And this brilliantly illustrates the actual math driving that closed-loop tracking. The pointing error is simply the difference between the reference angle and our measured angle. But that standard servo correction law, that is where the real magic happens. The proportional, integral, and derivative values, those K variables, well, they act kind of like a highly trained race car driver. Instead of violently jerking the steering wheel to fix a swerve, this math calculates exactly how aggressively the Jitterbug hub needs to smoothly adjust its mirrors to fix the pointing error. It is just a constant mathematical battle against drift. All right, Section 5, battling atmospheric disturbances. Make no mistake, the atmosphere is the absolute biggest risk for free space transmission. We're up against a whole host of physical threats that can distort or just outright block our photons. Turbulence and thermal gradients bend the light. Scintillation causes these rapid fluctuations in signal intensity. Fun fact, this is actually the exact same physics that makes stars look like they're twinkling in the night sky. We also have to deal with beam wander, where the beam physically drifts off target. And of course, there's absorption and scattering caused by everyday things like fog, rain, dust, and haze. To mitigate all of this, the system has to rely heavily on adaptive optics and incredibly narrow beam divergence. We can actually quantify this battle using the total atmospheric transmission efficiency formula. The overall efficiency is a product of all these different environmental factors multiplied together. You've got turbulence efficiency, scintillation, absorption, and beam wander. If literally any one of these drops significantly, your total atmospheric transmission just plummets. This is exactly why having that beacon-assisted reacquisition and advanced environmental filtering software is absolutely crucial to keeping the link alive. Let's look at Section 6, Deployment and Laser Safety. If you were to somehow pack this whole thing up and deploy it in the field, this is the hardware you'd actually need to bring with you. You've got the beacon source living over on the Solstice node. On the jitterbug side, you have the telescope, the beam steering mirrors, and those fast-tracking sensors. You also need a dedicated real-time control computer to run all those heavy servo equations we looked at earlier. Plus, you need optical filters to suppress background light, the atmospheric compensation software, and incredibly stable power and synchronization electronics. All of this ensures your single photons trigger exactly when they're supposed to.
So the crucial point is this. When you are operating high-precision optical hardware out in an open environment, safety is absolutely paramount. The manual is very clear on this. Strict laser safety controls, absolute beam containment, and clear line-of-sight operating procedures are completely non-negotiable. If you deploy this outdoors, strict weather and visibility limits must be documented and adhered to as part of the safe operating envelope.
To wrap up everything we've covered today, I want to read you this polished manuscript wording directly from the source material because it just perfectly summarizes the whole technological architecture. Quote, "The Jitterbug Hub maintains free space optical communication with the Solstice node through a beacon-assisted telescope link. The Solstice node provides reference illumination and lock feedback, while the hub manages pointing, pulse timing, and tracking correction. A closed-loop servo system compensates for atmospheric turbulence and alignment drift, enabling stable optical transfer under variable conditions." End quote. It is just a beautiful piece of engineering, and it leaves us with an incredibly exciting thought to close on. If a closed-loop servo system like the Jitterbug Hub can successfully guide a single photon through a turbulent, chaotic storm and hit a moving solstice target, what does this technology mean for the future of deep space communication? I mean, if we can master the atmosphere, the vacuum of space is next. Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you in the next one.